we are now going to talk about some more features that alkynes can participate in, but only if they are terminal alkynes. That means if they're at the end of the chain. So here's a table of the acidity of hydrogens that are on carbons in various states. So the approximate pKa of a terminal alkyne in acetylene is an example. This CH bond right here's pK is about 25. If you look at an alkene, any one of these CHs in this example are the same, pK of about 44. For an alkane, and this is an example, CH about 60. So people wondered, why is there this trend? We need to explain why this is. And one reason that people think might be the cause of this trend is how much S character there is in the orbital. In other words, think about it. This carbon is sp hybridized, which means that the orbital that it's using to make the bond with the hydrogen is an sp orbital overlapping with the 1s orbital on the hydrogen. So if that bond ionizes, the hydrogen goes off as a proton. Remember, that's what it means to be a bronzosylary acid, is that it donates a proton, leaving behind the pair of electrons. So that pair of electrons has to be in an orbital. So the orbital that it would be in is an sp orbital on that carbon. And so the idea is that that orbital is made up 50% of an s orbital and 50% of a p orbital. So we would say that it has more s character than a similar situation with this guy. This carbon is sp2, so if you take off a proton off of here, then the negative charge, the pair of electrons, will then be in an sp2 orbital, which is only 1/3 s in character and 2/3 p in character. And these guys in alkanes are sp3, so the negative charge has to be in an orbital, an sp3 orbital, which is only 1/4 of its character as s. And the idea is that, well, maybe that the more s character, the tighter toward the nucleus it holds the electrons, that might be better for those anions. And like I said, we're trying to explain an observed trend, and that's an argument that is as acceptable as anything else anybody has come up with. So that's what is thought to be the reason. Now, I will point out that none of these things are very acidic in the grand scheme of things. I mean, think about it. Water's pK is about 16. Hydrochloric acid is negative something. So they're not really acidic in that sense, but we're just talking about relative to each other, we see this trend. And if we look at any acid, we also know something about the conjugate base. So if we look at finding a base that could pick off one of these protons, it's going to have to be a really strong base. In other words, something whose pK of the corresponding acid is more than 25, because the weakest of these acids is 60. The strongest of these acids is 25. All of them are weak compared to, classic acids, but that means that we're going to have something who came from an acid that had a larger number than at least 25 to get this proton off. So where do we find such a thing? Well, we've looked already when we were talking about the concept of acids and bases, we looked at the anion of ammonia. So ammonia's pK is about 35, and this is the anion from that. Remember, there's 2 unshared pairs of electrons on this nitrogen when it's an anion. The pK of ammonia is about 35. This anion's about 10 times stronger, 10 orders of magnitude stronger than this. So if we put some of this anion in the presence of this acid, quote-unquote acid, because it's so much stronger of a base than this one's anion, we could pick off that proton. And we did see examples of that when we first looked at acids and bases in Chapter 2. So here's a picture of that reaction. The pairs of electrons are shown now. So you get the sodium salt of this, and we would usually write it NaNH2 in order, but they're trying to emphasize here, this is the base. And this is a generic terminal alkyne. So if it's inside of the chain, there's no hydrogen. Okay, it has to be at the end of the chain. Then it has this hydrogen with this bond that, when it breaks, can accommodate, better help stabilize that negative charge. And so we can do an acid-base reaction and make this anion. So then the next question is, well, why are we interested in that? Well, in doing that, you've created a carbon with negative character, or a honest-to-goodness negative charge, and we have an opportunity to use that as either a nucleophile or a base. And it is basic. It's a good Lewis base, and would react with any acid that has a pKa less than 25. But if we find something else that we could react it with, we could use that to make a carbon-carbon bond. And if we need to do that, we need a carbon that's got positive character. So this carbon with negative character would be attracted to a carbon with positive character. So where could you find a carbon with positive character? Well, here's an example. If you have a carbon bonded to a more electronegative element, such as a halogen or an oxygen or even a nitrogen, you could have a positive character carbon. Now in this chapter, we're going to only talk about alkyl halides as the source of carbons with positive character. And if you were thinking about oxygens or nitrogens, that's fine. We'll talk about those later. Okay, but right now, all we're going to talk about are reacting these kinds of anions with carbons with positive character in alkyl halides. And I took the picture from the book and made it more generic. So we're not limited to one particular alkyne. We're not limited to one particular alkyl halide. So I have changed this to an R prime, and this is an R. So we could put together two chunks of carbon, and this is going to be the nucleophile, and it's going to substitute for the bromine, which is going to come off or leave off of there. And so we've done a substitution reaction. And one of the things that you might think about is this terminology where we talk about the organic molecule. We might call it a substrate, and it's undergoing a reaction. Now both of these pieces are organic molecules, so then the next obvious question is, okay, well, who is the substrate? And this guy is the one that's being acted upon, and this is going to drive the reaction. Remember, the electrons drive the reaction. So the alkyl halide is going to be the substrate. This is a nucleophile that's reacting with that. The bromine, in this case, is leaving. So we make this bond right here as our new carbon-carbon bond. And this stuff comes off, and the sodium is just simply a spectator. And here's another drawing showing that in a more three-dimensional way. And you notice that it's labeled here. I've added some words here to this picture from the book. So this is the substrate, and this particular carbon in this picture is primary. As long as the R right here is not a hydrogen, then it's primary. Now it would work if that were a hydrogen. It would be fine. But what it can't be is it can't be too crowded. So this substrate, and we're referring to this guy right here, has to be able to be approachable from the back side. You notice how they've drawn this coming in from this side, opposite to where the bromine is leaving. We're going to talk about that detail of that mechanism in Chapter 11. What you need to know right now is that this carbon in this substrate can't be too crowded. So it's going to work fine if you talk about a methyl bonded to a halogen, or a primary carbon bonded to a halogen. Sometimes secondaries work, but you kind of have to take those on a case-by-case basis. And here's a picture of the transition state. And again, we'll talk more about this in Chapter 11. But what they're implying here is that the nucleophile, which is this anion, is starting to make a bond with this carbon at the same time as this bond to the halogen, the leaving group, is starting to break. So all of those things are around this carbon at the same time. And if you're really paying attention, you have three just plain old bonds and then two partial bonds. And that's called a five-center transition state. More on that later. And so when we get done, we've now kind of change the orientation. If this was an R molecule, this is going to be an S molecule. And again, those kind of details will come out more in Chapter 11. What you need to understand right now is where is the new bond? Between which two carbons are we making a new bond? And this guy has to be an alkyl halide, and this guy had to have come from a terminal alkyne. So, let's go back over that. You have to have a terminal alkyne. In other words, it has to be at the end of the chain. So I've kind of highlighted that in red. And the pKa of those things is about 25. So if we put in a stronger base, such as the anion of ammonia, whose pK is about 35, we can make an anion out of this by picking off this hydrogen. And so here's our anion. And whatever the cation is, whatever came with this guy, which is usually sodium. All right? Now that can be a base or a nucleophile. We're going to use it as a nucleophile if we have a substrate carbon that isn't too crowded. And then we'll take the alkyl group that's in this substrate and we'll attach it to this carbon that's at the end of this chain. And what that will do for us is it will make us a bigger alkyne. So if you started with just plain acetylene, then you could make that into an anion with the sodium amide. And here's a generic alkyl halide. And so you make a bond between this carbon and this carbon, and there is still a terminal alkyne on the other side. So you can do this again. So you put in some more sodium amide and make your anion, and now we call this R prime, so it could be a different chunk of carbon. And unfortunately, they left out the CH2. I would have put the CH2 because they showed it here. That CH2 is really also still here. So they kind of cheated a little bit. There should really be a CH2 if you want to just take this one down here and keep going. Or you could just start with a brand new one. Okay, either way, you're fine. You can just make bigger and bigger alkynes as long as the pieces that were here were not too crowded. So here's an actual molecule. If you had this alkyne, it's terminal, and you treat it with your base, and then some other alkyl halide, you can make a bigger alkyl halide. Now it just so happens, this is 1, 2, 3, 4 carbons on this side, and we're adding 1, 2, 3, 4 carbons here. So we could have made this molecule by just doing this twice with acetylene. So if I put this and some of that together, then we get to here. And then we just do it again, we can get all the way. So here's a question, why doesn't this work? If we put this base in here with this is a secondary alkyl halide. Now remember, we're talking about an alkyl halide. Carbon has positive character, but it can't be too crowded. Alright, so this is observed. If you put this anion in with this alkyl halide, you get an alkene, and you don't get a substitution product. And it's part of this whole evidence that it can't be too crowded, or else it won't work. And what we'll call this is a competition between substitution, which is what we wanted, with elimination, which is what really happened. And again, there will be more discussion about that in Chapter 11. So, we're using this to make bigger molecules. Now, somewhere it might help if you kept a list of all the reactions that you learn as you go for making new carbon-carbon bonds. Because we're going to use those kinds of reactions to take small molecules and make bigger molecules. And so far, in Chapter 8, we talked about adding a carbon with a carbene onto an alkene to make 3-membered rings. So we had chloroform and KOH, which would generate the dichlorocarbene. And so then we could make 3-membered rings with that had chlorines on them. Or the Simmons-Smith reaction, where we use diiodomethane and the zinc-copper couple, and that made this species, which acts like a carbene that's just a CH2 carbene. Again, makes 3-membered rings, but they're just plain little 3-membered rings. Now you have, in Chapter 9, this new reaction which is the alkylation of terminal alkynes makes bigger alkynes. Now there's some constraints on that reaction. We've talked about the fact that the substrate can't be too crowded. That's fine. Every time we talk about making new carbon-carbon bonds, there's going to be, some little things that we need to know. How does that work? So if we're talking about synthesis, making small molecules into bigger molecules, we need to know what are the issues associated with doing that. And there are several things we're going to look for. Number one is the carbon skeleton. In other words, how many carbons do you need in your final product, your target molecule? And are there any rings? Are there any branches? Or is it just a straight chain? All of that is part of the carbon skeleton. And so if somebody walks up to you and says, I want you to make me this molecule, that's really the first thing you need to know is, well, how many carbons are there, and are there any rings or branches or what have you? And then the next thing that you need to know is, are there any functional groups on this molecule? Remember what we mean by functional groups. We don't mean like a methyl group or an ethyl group. We mean, are there any alcohol groups? Are there any carbonyls? Are there any halogens? Are there any double or triple bonds, and so forth? The ring idea, the branched chunks of carbon, methyls, and so forth, that's part of the carbon skeleton. The functional groups are all those other things that are different from just plain old sp3 hybridized carbons and hydrogens. So you not only need to know what functional groups are present, you also need to know where are they in your carbon skeleton. And if you were trying to make this molecule, you need to know, how to get them onto the right carbons as you go through the process. And sometimes you have more than one functional group, so then the question is, are they on adjacent carbons, or on the same carbon, or are they far away from each other? And all of that is some things that we may or may not know how to do yet, but eventually we will learn how to make molecules that have more than one functional group way far away from each other. We actually already do know a couple of reactions that will make more than one functional group at a time. Lastly, the hardest thing about synthesis, if you have to deal with it, is the stereochemistry. Now remember, stereochemistry includes not only stereocenters, where you have an R or an S molecule, but also geometry. Sometimes you have a ring with a cis or a trans, or you might have a double bond that's cis or trans. So if that's been drawn in your target molecule, then you need to know how you might deal with getting just the one you want, if you can, and not a mixture. And so in the process of choosing reactions that might enable you to create a certain functional group, you want to know, does it also control the stereochemistry? And we have talked about a few things that would, and some other things that could not control stereochemistry. So here's a question. Can you unmake scrambled eggs? And so think about that. If somebody hands you some scrambled eggs, you know where they came from, because you know how to make scrambled eggs. You know that somewhere along the way you had to have some eggs, and you had to have something to stir with, and maybe you wanted also some salt and some pepper, and you needed a pan of some sort to heat them up in. You know all the things that go into making the scrambled eggs. But what if you had to go and get the materials for that? Well, right now you can go to Super Walmart and you could buy everything you need. If you had nothing, you could go there and you could buy everything you need to make scrambled eggs, even a camp stove if you didn't even have a stove. But what if you lived 300 or 400 years ago? Then you'd have to go to more places. You might have to go to the farmer down the road to get some milk, and maybe a different farmer to get some eggs, and perhaps to the general store to get a pan. And you might have to go out into the woods and chop some wood so that you could have a fire, and so on and so forth. Everything has to be built up from what is available. And when we talk about synthesis problems, one of the issues is, what do we have available? Another thing is, what reactions are we going to use? When we talk about making scrambled eggs, we know that we have to break some eggs to make scrambled eggs. But if you thought about the opposite, could you unmake scrambled eggs? Well, the answer is, well, no, you can't cook eggs and then subsequently uncook them and put them back into the shell. So when we talk about reactions, you've seen this kind of diagram before. When we talked about taking an alkene and adding HX to it and making an alkyl halide, that was a reaction that would go from basically left to right. But if you had an alkyl halide, you could also dehydrohalogenate that, and you could go back from right to left. But you notice the way I've drawn this, these are not, the same reaction going back and forth, because it's completely different conditions to go from this way to this way versus going from the alkene to the alkyl halide. So it's kind of like the process of unmaking something. It may or may not be possible, and even if it is possible, it probably is going to take a completely different set of conditions or reagents to be able to do that. So when you think about a target compound, somebody walks up to you and says, I want you to make this molecule. Here's what you can start with. So that's knowing what sorts of things are available that you can apply to the problem of making this molecule. And so you need to pay attention to, okay, what sorts of reagents can I use to come from my available materials to get to the product molecules that I'm trying to make. And you don't have Super Walmart, you're going to be limited to what you can start with. And so here's kind of a description of what I was just talking about. Thinking about where are all the sources of all the carbons that you're going to put into your molecule. You may have to go back multiple different sources of carbon. And each time you have a problem, you need to read to see what your limitations are for what you can start with. And we're going to say, well, you can have some common materials, common reagents they're called. So if you needed some HCl acid, you could have that. If you needed some KOH, you could have that. If you needed some sulfuric acid, you could have that. But if you need a 5-carbon molecule, maybe you can have that, or maybe you can only have a certain type of carbon molecule and you have to show how to make that one into the one that you actually need. So that's where you have to be careful. And one thing you might think about also is kind of think about this like when you look at a river, a big river like say the Mississippi River, there's actually a lot of other rivers that flow into it. Some of them are really big. The Missouri, the Ohio, whatever. The Ohio River is made out of the Allegheny and the Monongahela, and they come together and they make the Ohio, and then it goes into the Mississippi. And there's all these little streams that go up to make all these little rivers. Well, when we first start talking about synthesis problems, we're not going to see a lot of different little streams coming together, but eventually we will. So when we say you need to show the source of all the carbons that go into your molecule, initially we don't know very many reactions to manipulate carbons, but as we learn more, we'll have fewer and fewer things that we can start with, and we'll have to get more and more details about how we prepare all of our sources of carbon from one basic type or a few basic types of carbon structures. So I'm going to give you a handout, or actually I'll post it, of problems, and so you need to read the rules, and the rules are going to be what kind of materials you have available to you. So at your store, however primitive it may be or how sophisticated it is, what you can use, you have to read about at the top of any of these problem sets. In the book, they have problems like this, and they might specify, start with a particular molecule, or they might say, how would you make this molecule? I'm going to say, here's a collection of things that you can have on the sheet or on the handout, on the homework, and you can use whichever of those things that you want. You can use several of them, only one of them, it doesn't matter. You just can't use any other source of carbon than the sources of carbon that you've been provided with. And also, when you're doing these kinds of problems, they're designed to get you to utilize the reactions that you have been studying. This is a pedagogical tool to practice the reactions that we're studying. So if you flip back to the back of chapter 19 or something later in the book and you find a handy reaction that you could use, I'm going to count that as wrong, because we're supposed to be using the reactions that we're learning right now and to see how to make them work, because that helps you to learn them. And I'm not the meanest person on the face of the planet. I'm not trying to get you to use stuff in the back of the book. I'm going to penalize you for using stuff that's not in the chapters that we're talking about right now. So just don't look, okay? Things will change over time for how is the best way to do something. We just don't know about those things yet, and so you can't use them. And as I said, let me reiterate one more time, every carbon in your target structure has to be accounted for within the constraints of whatever rules are given for the particular problem. So here's an example. Suppose that this is your target. So the first thing you do is you count the carbons, okay? So you count these carbons and you find out that there's 8 carbons. And let's say in the synthesis problems, none of your starting materials can have more than 5 carbons in them. So obviously, since your target has 8 carbons in it, you have to have made at least one new carbon-carbon bond. And remember we reviewed what our possibilities were. One of our possibilities was a couple of little reactions from chapter 8 that would make cyclopropane rings. That doesn't look particularly applicable in this case because there's no little cyclopropane rings in here. So perhaps, there's something else. Well, then the next thing you're going to see is, well, there's no triple bond either. So, what's up with that? Well, what about this alkene? Don't we know a way to make an alkene from an alkyne? You could take a triple bond and make it into a double bond. We did talk in this chapter about doing that. And not only that, if you look at this, there is some stereochemistry. This is particularly a cis double bond. And in fact, in this chapter 9, we did talk about making specifically cis alkenes from alkynes. So there may be something to that. So we're seeing this with no triple bond in it, but now we're starting to think, oh, these 2 carbons right here could have been the 2 carbons that were originally part of a triple bond. So that tells us that if we want a cis alkene, we're going to reduce the triple bond to the double bond, the cis double bond. But you can't do that until you're through making your new carbon-carbon bonds. Why not? Because the only ways that we know to make new carbon-carbon bonds is from a terminal alkyne with an alkyl halide, or for making cyclopropane rings, okay? So you have to have a terminal alkyne in order to make a new carbon-carbon bond. And we have to make a new carbon-carbon bond because we're going to be limited to molecules that only contain a maximum of 5 carbons. So we know there has to be at least one new carbon-carbon bond formed. Now let's look at this some more. So which one is it? Well, you could go 5 plus 3, but look at this. We know this has to have been a triple bond if we're going to make this cis alkene. So we could make this bond, but then we would have a 6 plus 2 problem. But we could also make this bond over here, right here, and if we did that, then we could have a 4 plus 2 plus 2, and so actually we could make both of these 2 bonds. So let's see kind of how that looks. If we had this alkyne, we could use Lindlar's catalyst, and that would give us our cis alkene. So then we look, okay, well this is not one of our allowed starting materials. We know we have to make a new carbon-carbon bond. So that's not available, so we have to make that. So we could make this one from here, And so we could be making this bond right here. So what do we need? Well, we just learned that reaction. We need sodium amide, and we need a 2-carbon group attached to a halogen. Okay, so perhaps bromine. So that would work. Is this an allowed starting material? Well, no, because it contains 6 carbons. And so we have to show where did that come from. And so we can do the same thing. We can start with acetylene, and we can take this sodium amide again, and this 4-carbon alkyl halide, and we can make this larger alkyne. Now, in your problems, you're going to have been specified that you could start with acetylene, so this is acetylene, and you could have started with alkyl halides of 5 or fewer carbons, and these are both alkyl halides of 5 or fewer carbons. So then we're good. Also, did it matter if I put this chunk of carbon on first or this chunk of carbon on first? No, it doesn't matter. I just picked an order. If you put this one on first and then you put that one on first, second, that would be fine. Okay? So there will be a handout, a set of problems posted in here that you can look at, and so this particular problem is an example that's kind of like the problems in row D. Here's another example. Suppose we look at this, all right, and we look at the carbon skeleton first. You count the carbons, there's only 5 carbons, so this time maybe you don't need to make any new carbon-carbon bonds. And so what do we know about making, this is a ketone and this is an aldehyde? Well, we've only had one type of reaction so far that would be able to make aldehydes and ketones at the same time. You notice that these guys are kind of far away from each other. And so we did have another reaction that could make aldehydes and ketones. If you had internal alkynes, you could make ketones. If you had terminal alkynes, you could make either aldehydes or methyl ketones, but that didn't make them far apart, and that was just in one molecule. So there's kind of a hidden agenda here, and it's kind of related to this oxidation. If I could take a single molecule and oxidize it with ozone, that would let me make an aldehyde, but remember, these two guys have to have been hooked together. So you see that? I could have had a ring. And those are the 2 functional groups that are present, so that's where I'm thinking about this. And so if we had this ring, we could open this ring up with this kind of reaction. And so then the question is this an allowed starting material? Is this an allowed chunk of carbon? And so you have to, again, look at your instructions and see. Now, different rows of problems have different allowed starting materials, and some of them you were allowed to start with an alkene of 5 carbons or less. And sometimes you had to use an alkyl halide as your starting material. So this one, I think, might be on a row where you could start with an alkene. And remember, the ring is not a functional group, but the instructions will say that you can start with a monofunctional alkene or a monofunctional alkyl halide. What that means, mono means 1. So it has 1 functional group in it. In this case, it's an alkene. The ring is not a functional group. Alright, so if your row said alkenes, then you're done. If you had to start with an alkyl halide, then you could have done that as well. You could say start with this alkyl halide, and you could do a dehydrohalogenation on that. Sorry. So whichever kind of problem you had, if this had to be your starting material, you would start with this. If this was allowed, you could start there, but you see it's not a problem either way. So generally, general comments on synthesis. I mentioned this earlier. The book has problems in it that usually tell you exactly what to start with. The kinds of problems that I'm going to give you, usually I give you a selection of things, of the kinds of things that you can start with, but they're not specifically laid out. Occasionally I will say you have to start with something, but most of the time, the kinds of synthesis problems I use, you have to decide. You can start with whatever you want as long as you follow the rules. And if you have a problem, either one of these problems or the book problems, it shouldn't take you all that many steps. Usually 2 or 3. And by the way, I'm not counting, sometimes you have a reaction where it says something like, remember the mercuric acetate where it said reaction number 1, you put in the mercuric acetate and the water, and then reaction number 2, you put in sodium borohydride. I'm going to count that as all one thing. So if when I'm talking about 2 or 3 reaction sequences, then those two processes to accomplish one transformation, you're basically going to have 2 or 3 transformations. Sometimes it's only one. Sometimes it's more. But you shouldn't, in this stage of the game, need more than 5. The ones that are going to be the hardest are going to be the ones where the stereochemistry is specified. Those usually take a few more steps. And when you get a grade, it's not going to be based on really how efficient you are. In other words, if it took you 7 reaction sequences to do it, and it could have been done in 2 or 3, it's all right. I'm not counting you on efficiency as long as each step that you chose was accurately chosen. But if you, say, ignored the fact that you were supposed to be making a cis-alkene and you did a dehydrohalonation and you didn't even comment on the fact that the cis-alkene would have been part of a mixture, placement of the double bond, or a mixture with trans, you could have all kinds of mixtures and you just didn't even talk about that. Or if you do a process that does create mixtures and you choose the minor product and you keep going and again, you don't even mention the other product, then I'm going to count off for those kinds of things. So in this chapter, your job is to know how to name alkynes, and they may be either by themselves or also with alkenes in the same structure. They may also have stereocenters in the molecules. Any of those things that we've had already could be in there. You now should know how to prepare alkynes from double dehydrohalonation or from vinyl halides. And those things create the triple bond where you didn't already have them. Or if you have a terminal alkyne, then you can make larger alkynes. And of course, we also talked about the reactions of alkynes that were kind of like alkene reactions, electrophilic addition reactions mostly. So we did double hydrohalogenation, double halogenation, and also hydration, which led to those interesting other results, the vinyl alcohols, which end up as either ketones or aldehydes. So whether you choose the mercury catalyzed hydration or the hydroboration, you get either the same molecules if they were internal or different if they were terminal. And you should start some kind of list somewhere on reactions that make new carbon-carbon bonds. And you might also have other lists that say, talk about ways to make other functional groups. We'll keep adding to ways to make alkenes, for example. We'll see some other ways to make alkenes down the road. We've already seen in this chapter ways to make alkenes that was added to the reactions that we already had to make alkenes in chapter 8. So any ways that you organize your thoughts, the more different ways you organize your thoughts, it's kind of like keeping your file straight in your computer. If everything is in one folder in the root directory or whatever, it's really hard to find stuff. But if you had everything in My Documents, still it's pretty hard to find things. But if you make subfolders and you keep things organized, then it's easier for you to call something to mind when you're trying to think of it. So that's another way to study. And that's the end of this chapter.